Hi, thanks for joining me today. I'm going to be going over problem 1 from week 7 of the Michaelmas term invariance puzzle competition. As always, I'll leave a link in the description below with details of the competition. Okay, so this problem here is sort of split into two different parts. I'll firstly read out the whole problem, then give you a chance to have a go at the problem, and then go over part 1 and then part 2. Okay, so the first part, we want to prove that there exists a function capital F defined on the space of continuous functions on the bounded interval 0, 1. So in other words, capital F takes in a function which is continuous on 0, 1, and capital F splits out a real number, and it has the property that capital F of little f is strictly less than capital F of little g whenever f is less than or equal to g and f does not equal g. Okay, so that's sort of the first part, and the second part, we want to know, does such an f exist if we change the domain to the set of monotonically non-decreasing functions on the closed interval 0, 1. Okay, so now instead of looking at continuous functions on 0, 1, the second part we're looking at monotonically non-decreasing functions on 0, 1, which aren't necessarily continuous, and we want to know if such an f exists. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the first part, there are quite a few different functions capital F we can use, but perhaps the simplest and the most intuitive one to use is capital F is the integral. So in other words, if we have a function h, which is continuous on 0, 1, so in other words, h is in our domain, then define f of h to be equal to the integral from 0 to 1 of h of x dx. Okay, firstly, let's check that this is nice and well defined, and that's quite immediate from the fact that h is continuous and we're looking at everything on a closed bounded interval, so this is nice, integrable, and this will be a finite number as well. Okay, in other words, a real number. Now we need to check that capital F satisfies two properties, so in other words, if we have f and g continuous functions on 0, 1 with f less than or equal to g on 0, 1, but f does not equal g, then we need to show that capital F of f is strictly less than capital F of g. And to check that, I'm not going to prove it too rigorously, but you can just sort of sketch yourself a diagram, and if you want to prove it rigorously, you just have to use a bit of analysis. But if we have f is less than or equal to g, but the key point being f does not equal g, there must be some point x0 where f of x0 is strictly less than g of x0. Okay, so there exists x0 such that f of x0 is strictly less than g of x0. Okay, so we could have, say, this point here, x0, and f of x0 is, say, this point here, and g of x0 is, let's just make it really big. Okay, but the key point now is that because f and g are continuous, there's some small interval around f and g for which f is strictly less than g. So in other words, there's some small interval here, and this whole interval here I'm going to call e. So there exists an interval e such that f of x is strictly less than g of x for all x in e. Okay, and this follows from continuity. And now the rest is somewhat trivial. Let's rub out what we have at the top and prove that capital F of f is less than capital F of g. So capital F of f is simply the integral from 0 to 1 of f of x dx. Okay, but of course we can just write this as the integral over e of f of x dx plus the integral on 0, 1 without e of f of x dx. Okay, but because f is strictly less than g on this interval, and f and g are nice and continuous, and e is measurable, I should say, it's an interval, we can write this as, this is strictly less than the integral on e of g of x dx. And of course, on this other interval, the complement of e, we don't know if f is strictly less than g, but we do know that f is less than or equal to g. So this thing here is less than or equal to the integral of g of x dx on 0, 1 without e. But of course, combining these two intervals, or these two sets, we're going to get the interval 0, 1, so the integral from 0 to 1 of g of x dx, but that is precisely just f of g. Okay, so we have that capital F of f is strictly less than capital F of g, so that solves the first part. Now let's move on to the second part. Okay, so the solution to part 2 is no, there does not exist a capital F when we change our domain now to the set of monotonically non-decreasing functions, and to prove that, I'm going to do it by contradiction. Okay, so we're going to suppose a capital F exists with the properties on. So capital F is a function from the set of monotonically non-decreasing functions, and it has the property that if f is less than or equal to g, and f is strictly less than g, then capital F of f is strictly less than capital F of g. Okay, now what we're going to do is define two functions, f of gamma and g of gamma, where gamma is just some generic number between 0 and 1 inclusive. So f of gamma and g of gamma are defined as follows. So f of gamma of x is going to be 0 on the closed interval 0 gamma and 1 on the half open interval gamma 1. Okay, and g of gamma of x is defined very similarly. It's 0 on the half open interval 0 gamma and 1 on the closed interval gamma 1. So the only point which they differ at is at gamma. So everywhere, for all x, a member of 0, 1 without gamma, f of x equals g of x, but, or I should say f gamma of x equals g gamma of x, but 0 is equal to f gamma of gamma. So when we evaluate f gamma at gamma, we get 0, because gamma is in this interval here, but that's less than g gamma of gamma, because that is equal to 1. Okay, because g gamma of gamma, we're looking at this interval now, so it's 1. Okay, so we have functions f gamma, which is going to be less than or equal to g gamma, because it's equal everywhere except at this point here, where it's different. But of course then, because it's different at one point, f gamma does not equal g gamma. Now the reason we can't just use the capital F we used in the first part was because, well, if we did use capital F here, the integral from 0 to f of f gamma is going to be the exact same thing as the integral from 0 to 1 of g gamma, because they're exactly the same almost everywhere. Okay, so we can't use that capital F. But what we're going to do now is derive some inequalities on this new capital F, which we're assuming exists, and then we're going to result in a contradiction. Okay, so now suppose we have two numbers in 0, 1, distinct, alpha and beta, and alpha is strictly less than beta. Then I claim that we have this inequality here, f sub alpha is less than or equal to g sub alpha, which is less than or equal to f sub beta, which is less than or equal to g sub beta, with none of them equal. Well, certainly this thing holds and this thing holds by the argument we just had with gamma. And I guess the only thing then we need to do is this thing here, that g of alpha is less than or equal to f of beta. But because alpha is less than beta, then that means that they differ in that small interval alpha beta. Okay, so this inequality holds, but notice that none of these functions here are equal. Okay, and then thus, because we're assuming some capital F exists, we have capital F of alpha is strictly less than capital F of g of alpha, which is strictly less than capital F of beta, which is strictly less than capital F of g of beta. Okay, but in particular then, that means that for any real number in 0, 1, say alpha, we're going to have the set f of alpha, f of g of alpha, and this set here is always going to be disjoint from this set here. So if you consider this set here, f of beta, f of g of beta, these two sets are always going to be disjoint, because obviously the last point in this interval is f of g of alpha, but that's strictly less than the first point in this interval here. Okay, so we have a collection of these sorts of intervals, so we can call this set here S. S is going to be the set of f of gamma, comma, f of g of gamma, for which gamma is some number in 0, 1. Now firstly, the cardinality of S is uncountable. S is uncountable, and the reason for that is, well, because S has a one-to-one correspondence with the closed interval 0, 1, which of course is uncountable. So we have that S is uncountable, but by this argument here, S must be countable, because if we sort of look at each of the components of they're disjoint intervals on the real line. Okay, so I actually just filmed a little piece claiming to prove that S was countable, but I realised when I was editing my proof was invalid, so let me quickly edit that. I claim that the disjoint union of open intervals on the real line must be countable, and the reason for that is, so suppose we have a collection I of intervals, so I is a collection of intervals which are disjoint and open. Well then for each I, for each, say, interval I, in I, we can prescribe a rational number q of I. There exists a rational number q I, which is in the interval I. So qi is a member of I. And the reason for that is each interval is non-empty. I guess we should perhaps have stated that, but I is a collection of non-empty intervals, and qi is a rational number in the interval I, and that exists because each of the intervals in I are open, and thus it follows that the cardinality of I must be less. Oh, by the way, this qi here is unique. So if qi equals qj, then it follows that I equals j. Okay. That's not too difficult to see because they are disjoint, and thus it follows that the cardinality of I must be less than or equal to the cardinality of the rationals, but of course the cardinality of the rationals is countable, so that means that this thing here is also countable. Okay, and of course we just apply the argument but swapping I for S, and thus we deduce that S is countable, but by the previous argument S is uncountable, and that's where we arrive at our contradiction. Anyway, I hope you have enjoyed this video. Two different solutions to two different parts. The first one, I guess, is slightly easier, and the second part uses quite a nice argument. Anyway, if you are new here, please do consider subscribing and checking out some of my other fun maths videos. That's all for today. I will catch you in the next one. Have a great day.